Stay safe. Okay. On Friday, we had just finished up talking about density dependence. So we've been sort of building up this conversation about how our populations grown and how can we track their abundance. So we started out sort of the most simply. Okay? What are the pieces or the factors that allow for population growth? When we talked about things like competition, okay? Then we added in the pieces of the life table. We talked about birth rates, death rates, fecundity, survival rates. Then we started talking about some equations and the pieces that go into that. We talked about lambda and R and the difference between those. So discrete versus continuous growth, which has a lot to do with the organisms that they're applied to. Okay, so a lot to do with things like breeding season and group type. And then at the very end of class on Friday, we started to talk about density-dependent versus density-independent regulation. So for the first time, beyond just general survival, we started to look at, okay, so populations can't in fact grow forever. Okay? So how exactly can we understand these factors like competition, right? And how that they affect what population growth looks like. And so remember, density independent, okay, are factors that have no pattern, okay, on population growth, right? So they affect population growth, but it's very random. Whereas density dependent, like we see in our graph here on our fuzzy plant, right, are factors that do affect overall survival in a predictable way. Okay. So this can be things like crowding and competition. Okay. So when we looked at this, we suggested things like having to compete for sunlight or having to compete for water and nutrients in the soil. Okay. Is probably why anything over that 200 or 300 per meter square does not work out great for survival on this planet. As we think about then density dependent regulation and these other factors that we talked about at the very beginning, we come to sort of the crux of the conversation. Okay? What do we actually do with that information? Okay, what is this as we think about how have we been laying out this information in sort of a calculable or graphical standpoint? We call that carrying capacity. All right, so carrying capacity is sort of like from the environmental standpoint. Okay, so literally the capacity at which the space these organisms find themselves in, okay, can no longer hold more. I think like a full basket. Any more organisms are added to that basket, they just fall out. So carrying capacity is our maximum population size. Okay, from a calculation or a graphical standpoint, we can visually see then, let me see our arrow here. All right, well, apparently we're using the crayon today, I don't care. what that carrying capacity is. Okay, so we're going to just draw a line. Where is our basket full at? We can't put any more organisms in our basket. So we call this logistic growth. But as we can see from what has happened to our graph, that more than just adding a flat top has happened here, right? So remember before, yellow is terrible at times, that all of our graphs, right, for lambda and for r were very J-shaped. Still erasing. Probably not literally. Didn't go down at the bottom. Okay. Very exponential in shape. We saw here, okay, in its own way, that was really expressing that infinite population size capacity. And even if we were to take this graph we had originally been using, and flat top it, we can already see that there are some subtle differences here. Okay. We don't have that straight up bit going straight to that carrying capacity. Okay, that straight up J is gone. Okay. Instead, with our logistic growth, what we have is a much stronger flattening of the line of the J, whatever we want to call that. Okay, so we can see that slowed growth. In other words, we see these effects of these density dependencies. Okay, so differences in growth rates depending on the population size. So here's what tends to happen. If we imagine our graph, okay, it almost ends up looking, that's a little rough. Oh, yeah, it's a little bit better. Okay, like you pulled an S and stretched it out, right? So you have periods of very fast population growth. Okay, particularly when the population is first starting out. And that makes sense, right? That was what we talked about on Friday. But as we start to approach, right, here's our flat population. So this must be carrying capacity. So as we approach that carrying capacity, okay, we can start to see that stretch. Okay, so we've slowed down our growth rate. If we think about this graphic, right, we've added less individuals each year on the top of that compared to, okay, down here when we had much bigger vertical jumps. And so in other words, at the bottom of this graph, it looks much more J-shaped. Much more like what we were drawing last week than the top of this graph, where it looks like we pulled on the top. It's like taffy. We pulled on that, stretched it out. Maybe at the bottom we were adding, I don't know, 100 or 200 individuals per year. But by the top, we've slowed that down. We stretched that out. Maybe we're only adding 50, and then maybe only 20, and then only 10 per year. Until we get to the top here, we're not adding any or very few. Right? This is net, right? Remember, we're talking birth rates minus death rates. So population overall size. Net size. When we say this. Certainly when we say the population size is staying at 1,000, that wouldn't mean nobody is born, right? That would just mean the number of individuals born is replacing the number of individuals that have passed away. Okay, so this is the most realistic representation that we've seen so far. This takes into account all of the factors that we've discussed. We have birth rates, death rates, survival rates, fecundity rates, and the fact that the environment is in here as well, right? All of those, density-dependent factors. This idea that we know that we cannot have a population that can grow to 1 million. Or infinity, right? Something will eventually stop it. Any questions so far? Okay, so let's look at logistic growth. In other words, the growth that's associated with this carrying capacity. How do we get that stretched S? Okay. Now again, remember, we're not ever going to derive these equations. Okay? We'll just look at them compared to the ones we had before. Okay, so fundamentally, okay, we're looking at the same kind of equation we had with R. Okay, and that's because R is a lot more flexible than the lambda one is. Okay. So ultimately what ends up here is we've added this business. Okay. So we still have N being our population, just like it has been in every equation up to this point. We've added this new factor, K. Right, so K is what's referencing our carrying capacities. This is going to be different for each new environment that we're in. Okay, so this is basically reflecting the size, shape, resource capability of that basket that we're talking about. Okay, so as we look at this then, as N gets bigger, in other words, as populations get more dense or larger, our overall growth rate, Okay, so in other words, the solution to this equation, my handwriting is really atrocious today. I didn't make it better at all, did it? Okay. The overall growth rate is going to get smaller or slows down. Okay, why? What's going on here? Because in the past, okay, if we had ignored this whole business, right, as n got bigger, our growth rate got bigger, right? That's how we have that exponential equation. So what's changed now? Why, as n gets bigger, does the growth rate get smaller? Right, so with our carrying capacity, from an application standpoint, this means that we're getting limited space and limited resources. Okay, so mathematically, how this turns out, okay, as n gets big, definitely drawing, n gets big, and we have a big number on top. Okay. This number will approach 1 here, right? Our divisor sign. Okay, the bigger n is, okay, the closer to 1 that n over k will be. Everybody see that? Okay. So the closer this is to 1, okay, the smaller this whole thing will be. Right? So basically 1 minus 0.99, for example. So what happens if I take Rn times 0.1? That's going to be a really big number. Doesn't even matter what all this business is, right? That's going to be a really big number. No. Then what if it's 0.01? Smaller, right? So the bigger n is, right, the smaller this decimal becomes. And maybe it becomes 0.01. So we end up with very, very small growth rates the bigger that n becomes. Okay, because that n is putting more and more pressure on that k. Okay, so that's what we see in this curve here. Okay, those slower growth rates are reflective of that n being bigger. You're putting lots of pressure on that environment. Okay. This number being very, very small. In other words, our growth rate becoming very, very small. That makes sense what's happening there? That's about as mathy as we're going to get with it. Okay. So we can see then, as our n gets really, really big, how we start to approach this 0 number. Okay. As this decimal gets infinitesimally small. Any questions so far on what we're doing? All right, so keep in mind, all right, both ways go here. So we just talked about n being high, that's this bubble. When density increases, our growth rate is approaching 0, right, because n's getting big. But the opposite works as well, too. When n is small, okay, we get a number close to 1 here. Right, because 1 minus what is fundamentally 0. The smaller the number we have here, okay, the closer this will be to 1, right? And the closer this is to 1, then the more of this equation we can ignore. In other words, the closer this comes to just being r times n. That's 1. In other words, just that exponential equation that we had a few slides ago. If we had 1 minus 0.0001, then it's pretty much just 1. Okay. That's if we had a very small n. We could have a good exponential growth in those cases. In other words, what our bottom of the graph looks like, right? Ish. It never looks like true exponential growth. And that makes sense because this is never completely 0. We never have a population size of 0. Right, so it's always going to be 1 minus something, even if it's just a really small number. But we get good exponential growth at that bottom of the graph. Then as our n gets bigger, right, as n grows, right, the n over k also grows. Right? So 1 minus n, k gets smaller. And when you multiply by a small number, you get a small growth rate. Okay, so in this way, this is how we end up with a growth rate that is inverted to the size of our population. Of course, this then is the top of the graph. The more n grows, the further up the graph we go. Right? So the slower and slower our population growth gets until it stops completely. Okay. That n is equal to that carrying capacity. Because if n equals k, n divided by k would equal 1, right? So 1 minus 1 would be 0. So r times n times 0 would be 0. That's where our growth rate would get 0. We smack that carrying capacity right in the face. We get a flat top on our graph. Our basket is full. Does this relationship make sense? About the only time in my life I can think that fractions really matter. My husband would be so psyched. Okay, so let's look at one example of logistic growth. Okay. So, U.S. humans. So if we look at U.S. humans, okay, we can track human growth rate, and we fit super well to the logistic curve up to about 1950. And a model was created for human growth in 1920. People dedicated their lives to this. All right, so all of the red dots and then ultimately the blue line was used in the model created in 1920. Okay. Super good fit. Now, after 1950, and then utilizing census data up to 2004, and obviously beyond, we jumped off the bus. Okay. Off the logistic curve bus. Okay. It looks borderline exponential. Very unlikely, but certainly not on any logistic curve anybody's been able to figure out since then. Okay. What happened in 1950 or around the 1950s that shifted us way off this logistic model? We certainly were fitting super well. So clearly we were on some carrying capacity that made sense. What changed? Something did shift in the environment. Does anybody know what the big change on the 1950s was? Again? Baby boomer. Well, sure, yes. What about them? So the war was, in fact, the big trigger to this. But what about it? Right? Because there were wars before that, right? There was the war in like 1914, 1915, right? World War I, right? We stayed on the logistic curve after that. We assume that daddy loved mommy then too. Why was this one different? What else came out of that war that was so important? Again? Partly the Green Revolution, but a different kind of revolution was really important here. The industrial. And along with it came sanitation and medicine. And more importantly, vaccines. Right? So people stopped dying. Right? So sanitation and medicine became significantly more accessible, right, post-World War II. As a result, right, survival rates, right, both in age and for birth, both for mothers and for babies, significantly increased. Okay. This is something we're going to get a chance to look at in lab. We're going to have a population demography, and you guys are going to get to look at longevity, basically before 1900 and 1920 and after, and kind of get a look at what is the big difference here. But so basically, as we saw big increases in medicine and care, hopped off the curve. At the same time, again, due to the Industrial Revolution, food and clothing became much more accessible, right? So as the cost of these things are really depressed, regular people could access them, and so people just stopped dying, right? They were able to care for their kids, more kids lived, and so we've hopped off our logistic curve bus, and we've never gotten back on, or not on an obvious one. So what we ended up doing in this case, right, was increasing the carrying capacity of our space, right? We increased the elbow room, we stopped spreading the disease, okay? We increased the resources, we were able to import them or build them. Then what? And this is one thing that sets humans apart, right, is we're ecosystem builders. And there are very few organisms that do that. It's not clear what the overall effect is. Okay, that is it for growth and regulation. Any questions before we kick the bucket on this one?